solving this problem, counting numbers, which is part of dynamic programming section in CSES. And the problem says that your task is to count the number of integers between a and b where no two adjacent digits are same. So we'll be given this range of a and b, and we need to basically find out all the numbers where the consecutive digits are not same. So basically, if we see, even 3 to 1 is a valid number itself, because there is no there is no adjacent numbers which is same, right? So all we need to find all these numbers which fit this criteria, that there is no adjacent digits have to be same. And if we look at the constraint, we have a very huge constraint. The range can be up to 10 to the power 18, and so obviously iterating over it won't be sufficient. So one might think that we can just iterate over the range, and then we can check for each of the number that if it has the adjacent digits or not, and accordingly count all those numbers. So if you look at the constraints, it won't make sense. It will give TLE for sure, right? So now we'll talk about like how we can use dynamic programming over here to solve this problem. Basically, this question is a variant of dynamic programming, which is digit TP. It is one of the pattern in dynamic programming, and it will help solving this problem very easily. Okay, so let's look at the example over here. So here we can see, let's suppose we are given L equals to 1 to 3 and R equals to 2, 3, 4. Okay, so the digit TP pattern says that it's a similar to other dynamic programming solution, which follows like recursive memorization, where first of all the given range is converted to a string. Okay, so let's suppose 2, 3, 4 over here is converted to a string. Then we do a simple recursion on each of the character itself, each of the index itself, and at each level, at each of the index, uh, we keep in mind that if it is a largest digit that we can pick or not. So for example, over here we see that we can only generate up to 0 to 2 as the first element in the, if you're trying to generate all the numbers within the range from 0 to 2, 3, 4, right? So in that case, we'll have maximum up to 0 to 2 elements in the first position. And if we are taking only 0 to 1, then in the second position we can take any elements from 0 to 9, and in the third as well we can take 0 to 9, right? But in case if we are taking the largest element, for example 2 over here, so that will be the maximum, because taking after 2, which is like 3, 3 will exceed this range, right? So we cannot take that. So if we're taking 2, then in the second position it again fixes the second position limit for the second position, which is 3. So we can take maximum 0 to 3 elements, right? And subsequently, since if we are taking 0 to up to 2, 0 to up to 2, then we can take let me modify over here. Yeah, we can take maximum 0 to 2. If you're taking from 0 to 2 digits, then we can take any number from 0 to 9 in the third position, right? Because it basically will always have a smaller numbers if we are taking one digit less from this second position, right? And if we are taking the largest digit that is possible, and the first position is also largest, in that case it also limits the third position as well. So we can only take the numbers from 0 to 4 itself, right? So that's what basically digit TP boils down to, where it maintains a tight parameter. Tight parameter is nothing but a flag which indicates that if you are taking the largest value, or is it the smaller than the current one, uh, smaller than the current position value, right? So in if we are taking the if the limit is set for that current position, then that case type will be 1. And if it is a smaller, for example, in this case, when we were taking in the at the initial for the first index, type will always be 1, but for the second one the type will be 0, right? Because we can take any element between 0 to 9. Similarly, over here, since we can take 0 to 2 elements, it type for the third position will be 0, but in this case, in the second position, type will be 1. Okay, we'll see how in the code it works. And basically, in our problem, it says that we need to find out all the digits where the adjacent digits are not same. So in that case, we also have to maintain what were the previous digit that we have taken. So for that, we also have to use another variable, which is previous digit, right, in the recursion. So basically, at the end, we have three varying parameters for the recursion. One is index, that will be going from left to right and will be generating all these numbers possible, and we'll check if the by matching the criteria the previous digit is not same, and we'll keep in mind the type as well. Yeah, so basically that is it. And yeah, we'll solve it. And before that, before going ahead with the solution, I would like to uh, recommend this channel. It is a really great channel for understanding digit DP, and I will link down the uh, video for the first introductory, which covers the concepts of it, into the my dis description, so you can check it out. It's a really amazing. You will understand this whole concept of type, index, and previous digits and all, right? Now, one thing we also need to keep in mind that while we are generating these numbers, since it can be used, we definitely have to do memoization as well, right? So for that, we'll be maintaining this memoization grid. Since there are three varying parameters, so we'll be taking three-dimensional DP for that. And for this DP will be of size. Here the size is, let's suppose in this case, maximum the length of the maximum numbers can go up to 18 digits. So you could, for safety, you could take the let's suppose whatever is the number, you can say n. Okay, you can calculate the by converting the number into a string and taking the length of it, so that will be n basically. So you can take n plus 1. And we also want to maintain the type, which will be of only size 2, because either it can be 0 or it can be 1. 0 means that we have not, the current position is not limited, and 1 means the position is limited, means we can take only up to 0 to 2 elements. In this case, type will be 1, and in other cases, type will be 0. But when we are taking 0 to 2 elements, in this case also the type becomes 1, and the third position type becomes 0. So that's how it will be. So it will be 2 only. And for the previous digits, so since previous digits can be between 0 to 9 only, and while initializing we'll take -1 while starting the recursion. So let's say we want up to 10, so we'll take 11 positions for that. And since -1 uh, we cannot access the grid using the -1 index, so we'll increment the offset by incrementing by 1. Okay, For each of the digit will increment by 1. So now let's look at the solution. Let me Okay, so let's look at this solution one piece by piece, so it will be a lot clear. Yeah, so as I mentioned earlier, so whatever will be yeah, and also let me tell you one thing. So since we wanted the answer within this particular range, so and the solution, the function that we have, it calculates the values between 0 to given n. So what we can do is we could call like solve for r, and we'll negate it with the solve of l minus 1. So that will basically give us the result. Okay. Here, as you can see, it first checks if the number given is negative, then it will return a 0 because there is it's not valid, n is not valid, and we are first converting into a string. Then we are checking if we are creating the DP, initializing the DP memoization. As I discussed earlier, it will maintain the last digit, type, and the index itself. We are initializing all the DP with the -1 itself, and then here we are calling the recursion, the DFS itself. So here we can see this is the part where it is checking if we have reached the last, we have processed the last index of this string. Okay, in that case uh, we have found one number like that which doesn't have adjacent digits. In that case, we'll return 1. And uh, if if the memoization has cache has value for these particular three variables, then in that case we are returning the cached value itself, and we are doing the limit as we discussed earlier, because we also have to uh, maintain a limit based on the type, right? So here I am taking bound as the name for the type, but it is the same thing. So we are checking if the current position is bounded. If it is bounded, then we have to take maximum value will be whatever is the current uh, uh, digit for this particular index. So in the first position it will be bounded, so the maximum limit is 2, right? So here it will give you the limit as true 2. But in the subsequent position, when we'll call for the sub problem, uh, it will become bond will become 0, right? So here is the result that will be getting for all the sub problems. So, and here we are checking if the previous that we have placed is greater than 0, and uh, and it is equals to the current one. In that case, we have to skip it because we don't want to count all those numbers where the adjacent elements are same. So we don't want to place the same digit again, right? So we want to skip it. And this is the next bound, means that the subsequent, what will be the uh, type for the sub problem, means the next position. So if it is like the bound is 1 for the current position, and the uh, it is checking if it is the limit one, the last maximum value of the current position, then the bond will be set for the next position. Otherwise, there will be no bond. As you can see in here, the second position has 0 to 9, freedom of selecting any element between 0 to 9. But if you are taking the maximum value 2, then the second position is limited, right? So that's what it says. If it is less than the limit, then the next bound will be 0, otherwise it will be 1. So here we are calling the subproblem itself. We are incrementing the index and then calling the next bound. And here it is checking that if it is I equals to 0 and previous is less than 0, it means it is checking the initial condition, right? That if it is just the start position, uh, then yeah, so it is basically checking the leading zeros itself. Okay, so here this part is taking in mind of leading zeros. So whenever let's suppose there could be one situation where the numbers are like this way, so 0, 0, 1. So even though it looks like it's not valid, one might think that we will not place 0 again, because if we skip it completely, then we'll not place the 0 again. So this number will never come into picture. So that's why we also have to keep in mind that this is a valid number. So how we can keep in mind that, we'll check if the current element is 0, that it means that the number that we are placing is 0, and then previous index, I mean previously it was placed is -1, means that this is the first time that we are placing, then in that case it will remain -1, means which represents that this is a leading zeros, right? Otherwise, if it is a situation like 1, 0, 1, and when we are placing 0 for the second time, we'll check if previous is negative or not. In that case, previous will not be negative, because in that case we'll be giving it whatever is the element as the previous. So 1 will be previous in that case. So that's why in that case I will become the current previous element. So in this case 0 will become previous position over, will go the position over here. And yeah, that's it. At the end we are memorizing the result itself. And yeah, so this is the position where it is calling. That's all. Hope it is clear. Thank you.